This is the third lecture for Chapter 2 for Stats 253, and in this lecture we'll discuss the measures of position, including the box and whisker plot. The related chapters in the text are sections 2.6 and 2.7 in Mendenhall. Now, the measures of central tendency answer the question, where is the data mainly grouped? Where is the average? Where's the median of the group? Where's the middle? What are the modes? The measures of variation answer the question, how is that data spread out with respect to the mean? Is it all clustered right near the mean, or is it sort of spread out all along the timeline or along the x value line? Okay, when you get to measures of position, you want to answer the question, how does this data value compare to other data values? Now, the first measure of position here I'm going to discuss is the Z-score, which actually seems like it's more related to the mean than it is to the to other data values. So the Z-score is a value that the original data value is transformed into. Right, that puts a preposition at the end of a sentence, which is bad, but okay, let me try it again. So an original data value is transformed into a Z-score, and here are the formulas for it. Let's just look at the one right here. The Z-score, you take the Y value that you have, you subtract off of it your mean, and divide by the standard deviation. Okay, now this is a very important transformation, and it's used extensively in the later chapters. It's used all the time, and let me show you why that is so. Okay, let's say I'll make two graphs here. Okay, this is my original data, and let's say it looks something like this. So it has a mean here at some number 17.25. And associated with this mean there's some standard deviation, and that's how the data looks. Okay, when you take all of the data values along here, well, these are the counts, you're taking these data values along here, and you transfer them into the Z-scores, this graph, sorry, that was an error, this graph starts looking, or turns into this. It turns into the same, so it's got a bell-shaped curve here, or Gaussian distribution, or sometimes called the normal distribution. It turns into what's called the standard normal distribution. In the standard normal distribution, the mean is at 0, so the mean is 0, and the standard deviation is 1. Right. By using this transformation, say you had a different one, so I've got this normal distribution. Using the Z-score, it's going to go into exactly the same standard normal distribution curve. Okay. The advantage of this is, you've probably looked in the back of your book, or maybe you haven't, but in the back of your book there are statistics tables. Now, they cannot make a statistics table for every single bell-shaped curve in the universe. 17.5, this one has for that one, this one has a mean, say, of -5. How can they make all these different distribution tables? So instead, they make only one, and it's the standard distribution table. Standard normal distribution. So whatever data you have in this, or whatever arrangement you have of data here, you transform it into the Z values, and then you can find the corresponding value of the table in the back of the book. There's other distributions besides the normal distribution. There's also T distributions, and that one also, it looks similar to the normal distribution, and it also requires a mean of 0 and a standard deviation of 1. To see that the mean is going to go to 0, let's look at that. Look at this equation right here. Let's say this Y value is the value here. It's the mean. Well, then Z is mu minus mu over sigma. 0 over sigma, it's 0. That doesn't prove anything about the rest of the points, but it does show you that whatever the mean is, it gets transferred into a mean of 0. So what does the z-score show in general? I just showed that the mean would go to a z-value of 0. Um, what if you had a different score? What the z-value then gives you is the standard deviations that the score is away from its mean. Okay, so you have a test score of 70, a mean of 65, and in this case, we'll say the standard deviation is 9. When you change it into a z-score, you find the z is minus 1.67. That means that the score is minus 1.67 standard deviations away from its mean. That holds true with the standard curve with the z's. It also holds true with the original curve with a mean of 85 and the score of 70. Percentiles are a very common measure of position. You see them in all sorts of standardized testing. The most interesting thing about percentiles from someone who's more in mathematics is that there are many, many ways to compute percentiles. Okay, so what is really meant by a percentile? Here's what a percentile is trying to convey. Recall a cumulative frequency. The cumulative frequency gave the number of people who scored less than, at, or less than a given score. The percentile tries to express the same information in percentage. So it's a percentage of the people who scored less than a given value. So a percentile is a percentage rank, right? Not exactly a percentage. It's something that's written in percent, but it means the number of people, the percentage of the people who scored less than a given value. Percentages have trouble, especially at the lower and higher end of data sets. Now, I didn't have much to say about percentiles, but I'll have more to say about quartiles. First thing I'm going to say is there are 3 quartiles. You might think there's 4 of them from their name, quartile, but there's 3 of them. And you start with 2. Quartile 2, Q2, is the median of the entire data set. Q1 is a median of everything below the median. Q3 is a median of everything above the median. So you have these 3 quartiles. They can, in general, depending on how percentile is computed, they can be looked at like this. Q2, the middle one, is probably at the 50th percentile. Q1 is probably at the 25th. Q3 is probably at the 75th. But I'm going to kind of leave that alone because I'm not saying a lot about percentiles since I don't want to get into all the different ways that they are computed. Okay. Now, once you have the Q1, Q2, and Q3, let's look back here a minute, you can then compute what's called the interquartile range. You might think this should say intra-quartile range, but it's called the interquartile range, and you get it by subtracting the largest quartile Q3 from the smallest, or the smallest one Q1 from the largest one Q3. And that's going to be used in a few minutes. And here is the main use for it, for that interquartile range. There are some points called outliers. Outliers are extremely high or low data values. When you look at the rest of the data set, they seem to stand out, and they don't seem to be in the huddle of most of the data values. Now, there's a judgment call as to what to do with outliers. Where do they come from? Well, somebody could have recorded the data erroneously. They could have had a dyslexia attack and flipped the numbers around. Okay, that happens to some of us all the time. So maybe it's just not correct. Another reason for an outlier is that perhaps the data was taken but not in the same situation as the rest of the data. So it actually represents a different experiment. So that's kind of interesting. In those cases, you might feel that it's justified to throw out the outliers and just work with the rest of the data, because in those cases the outliers really don't have much to do with the data. Right. However, you should just think in the back of your mind that the outlier might be where all the real science is. If you think of the history of physics, how does physics advance? There's something that occurs in physics and it doesn't quite make sense with how things are explained. It's usually presented as a paradox. And it is by that almost seems like an outlier. It's a little piece of data that doesn't seem to fit with everything else. But in looking at that, then we've moved forward and get things like quantum physics. So don't be so fast to just throw out outliers. Think about them first. Okay, so in order to find an outlier, we'd like to have some kind of a quantitative method to find them and not just saying, well, this looks like it's out of place. So what we use is we use the high and low data values. Here's the highest one and here's the lowest one. And we add various amounts of the interquartile range and we create what are called fences. And we look at what points are and how they fall within what is called the inner fence and the outer fence. Before we do that though, I want to mention what is called the 5-number summary. You can get this from software always likes to give you the 5-number summary, and it's a very good summary of the data. What it consists of is the minimum value, the minimum data value, the smallest one and the largest one, and then the 3 quartiles, Q1, Q2, which is the median, and Q3. Sometimes they also throw in the mean. In that case, I guess it's the 6-number summary. Now we're going to look here at the box and whisker plot, and I will show you how to construct these inner and outer fences. So if you want to do a box and whisker plot of data, you first find the quartiles and then you find the interquartile range. Okay. You construct values for what is called the inner fence and the outer fence. For the inner fence, you take the lowest value, the Q1, and you subtract 1.5 times the interquartile range. And for the upper part of the inner fence, or upper boundary of the inner fence, you take Q3, which is your highest quartile, and you add 1.5 times the interquartile range. That gives you an inner fence. For the outer fence, you do the same thing, but you use 3 times the interquartile range. Now you can use this information to draw the box and whisker plot. Q1 and Q3 are called hinges. So you draw hinges, which if you're doing a horizontal box and whisker plot, these are vertical. If you're doing a vertical box and whisker plot, these hinges are horizontal. Okay. So those are just the edges of the box. That creates the box by connecting those hinges up. Then you draw a vertical line through the box at Q2. Now you draw the whiskers. You start from the edge of the box, let's say the lowest data point and the highest data point, and of the box, Q1 and Q3, and you draw a line to the smallest data value that lies within the inner fence. And you start at the upper edge of the box and you draw it to the highest data value that lies within the upper end of the inner fence. All right. Any points that lie between the inner fence and the outer fence, you mark with some kind of symbol like an asterisk. Any points that lie outside the outer fence, you give them another symbol. These are definitely the outliers. These might be questionable. Okay, so here's just a generic box and whisker plot. This is a horizontal one. You could just as well have drawn a vertical one. All right, you see the hinges. Here's a hinge at Q1. Q1 is at 100. So just a vertical line at 100. Then you also see the hinge at Q3. Okay, and the Q3 was at 120. Then the box is created by connecting those hinges. Q2 is the line right down the middle. As you can kind of see, this is kind of a skewed distribution here. That line isn't directly in the middle, it just crosses the box parallel to the hinges. All right, the outer and inner fences aren't shown. Ooh, that should say inner. Okay, I just want to make a note here. People who haven't taken my classes before, I don't always go back and correct all my errors. The reason for that is that I just think that you need to see people making mistakes once in a while and correcting them and getting out of them, and that it's not a big deal. You know, if you have a real lecture, I'll be making mistakes all over the place and correcting myself and my speech as I go along, so you don't need to hear a robot speech. No, especially. So, at any rate, I don't correct all of them. I don't know if that's the reason or the rationalization, but at any rate, you can take that as okay, as an explanation. So this should say inner fence, and somebody cut and pasted way too much here. Okay, now the inner fence was 1.5 interquartile range distance away from the edges of the box, right? And it's not drawn on here. I'll just put it right here. So the inner fence was 70, and the upper part of it was at 150 right here. Okay. The whisker goes to the data values, that the smallest data value that lies within this inner fence. Maybe we need a line to show that fence. So, okay. So here's the inner fence. So you can see this must have been the smallest data value that was inside of the inner fence, and here must be the smallest, that was the biggest one. Here's the smallest data value that was within the inner fence looking to the south side of it. Okay, where's the outer fence? Let's get a different color for that fence. Okay, the lower outer fence was at 40, so I'm going to put a line here. At 40. And the upper fence was at 180. Okay, so you see here, these values are lying outside, beyond the outer fence. So here's some outliers right here. Okay, here's one right here, and you can't really see this that well, but here's another outlier here, and it's outside of the outer fence. Then these two are really plus signs, which you can't see at this resolution, and they lie between the inner and outer fences. So this point and these 2 points are really outliers. These, maybe they are. You might want to look at those. Okay, so there's your box and whisker plot. Now I'll show you one with some real data. So here's the number of elementary schools in 16 states. I think I got this example from that Blumen text that I talked about before. So that's Blumen Elementary Statistics, a step-by-step approach. It's a very good book. I use it in 252. Okay, so here's the data. I want to find the quartiles. So I have to line them up pretty much. So I line up all the data. Fortunately, the box wasn't big enough at the end to get the last data point. This is an even number of points, so the quartile, so the median is going to be an average. So average the two middle values and find Q2. Then I look at values less than that quartile, less than 655, and I find the median there. Again, it's even number. I have to average those, and going above Q2, I find Q3 as the average of data values 12 and 13 in this case. So Q1 is 457, Q2 is 655, and Q3 is 899. The interquartile range, I take Q3 and subtract Q1, give me 442. Now I create the inner and outer fences. The lower inner fence is negative. Well, that's not physical, so you can ignore it because you're not going to have a negative number of elementary schools in any state, so you can ignore that. Essentially, it should be 0. The upper inner fence is at 1591. Okay, now before we go any further, I look up here and see the biggest data value is 1196. It's inside the inner fence, so I'm not even going to bother with the outer fence. It looks like we don't have any outliers in this data set. So here's resulting box plot. Here was the median. Here are those hinges at Q3 and Q1. The whisker extends here to the smallest data value between the outside edge of the box and 0, because the inner fence was somewhere over here and had no meaning. And here is that upper value, which I think was 1196. And that's your box and whisker plot. Down here, because this is a horizontal box plot, these are your y values, are down here. What is over here on this axis? Nothing. It has no meaning. There's no scale here. And there's a reason for that. The height of the box has nothing to do with the data. It only has to do with how you wanted to make it so that it looks nice. If I made this box and whisker plot and I only went this high with it, whoops, well, went straight line, okay, and I went like that, and that was my box and whisker plot there, that was the box of it, it would be, well, hopefully it would be straight, but okay, sorry, kind of bent up there. That's the same box and whisker plot as the big blue box. It doesn't matter how high you make it. You just make it something that looks reasonable. So the height of it has no meaning to the data, and that's why there's no scale here. If you make a vertical box and whisker plot, the vertical axis will have the data values, but the horizontal axis won't have any. So a vertical one would look something like this. Here's, oops, here would be Q3, Q2 in the middle, and Q1 down here at this hinge, and then it's got two different color whiskers here. Alright, so on this axis is your Y values. This axis, nothing.